We live in a time of global transformation. The Energy Futures podcast explores how we can accelerate the expansion of clean energy technologies and reduce our reliance on fossil fuels. From heating and cooling our homes to moving around our planet and beyond, we bring together researchers, scientists, business leaders, and communicators to exchange knowledge and try to answer one important question. How can we create a sustainable energy future for all? This podcast is produced by Energy Futures Lab of Imperial College London.
AI is a leading force in the development of emerging technology, in day-to-day operations and addressing global challenges. But what is the environmental impact of AI? And does AI have a carbon footprint? Today's episode is hosted by Dr. Nadine Moustafa, a research associate at Imperial College, specialising in carbon management and decarbonisation technologies. Her guest is Hanya Ahmed, a postdoctoral research assistant at the Royal Veterinary College and Queen Mary University, with the School of Electronic, Engineering and Computing Science. She specialises in building and training AI models for industry and medical technology. Today they discuss what is AI and how to build an AI model, differences in AI technologies, the cost of running large data centers, and carbon accounting of AI.
Welcome everyone to today's episode of Energy Futures podcast. Today we'll be talking about a deep dive into AI and its sustainability. And I'm Nadine Moustafa. I'm a researcher at Imperial College London. I'm based both in the Chemical Engineering Department and the Centre for Environmental Policy. Today as my guest, I have Hanya Ahmed, and I'll let her introduce herself if that's okay.
Thank you so much for the introduction. So I'm Hanya Ahmed. I'm a postdoc researcher at RVC, Royal Veterinary College, and Queen Mary. I heavily specialize in computer vision and natural language processing.
I'll start today with a very simple question just to kind of set the scene. And I want to ask you to explain, what do we mean when we say AI?
AI is artificial intelligence, which branches off into multiple branches, which is computer vision, natural language processing, machine learning, reinforcement learning. But heavily what AI means is that we created models that mimic human intelligence using neurons, etc., to make a model that gives you predictions based off of the data that you provided.
And I think, so I know you've worked on a lot of machine learning models and within artificial intelligence and AI, and maybe you could kind of go through that with us today. Like, what do you do on your day-to-day basis?
So my work heavily spans quite broadly. So I can start with embedded AI for predictions of asthma attacks, as well as a bit more of computer vision, which is predictions and segmentations of medical image analysis for many different fields, where it was ophthalmology, cardiology, as well as radiology, and then now veterinarian for different equine objectives.
And maybe based on that, just to kind of expand on that a little bit, I know you build models and you train them basically to be able to do all of that, right? So when you talk about medical imaging, so you build those models, and how does that work? Like, how do you build a model? Can you maybe walk us through that?
So I get brought an objective, which means a clinician usually or a company comes to me and says, so this is our objective. And the objective is usually we want early detection of a specific disease that is either chronic or either causes a lot of deaths in hospitals or etc. And clinicians can't really detect it quite quickly because people don't come in except if they're feeling very bad, right? So we try to, a lot of the objectives is that we try to pick it up when they're having a normal checkup or a baseline checkup every 2 to 3 years. Not many people do their checkups regularly, right? So I get an objective of, for example, I want to accurately diagnose asthma, for example. So if someone goes in for a baseline checkup, which not many people do often, it takes a while, around 6 to 8 months, to get diagnosed with any type of respiratory condition, specifically asthma and COPD. So a company would come to me with that objective, with their respective hospitals or data, etc. I get given data, and then the output that they would want to show a clinician, basically, or to help doctors to decrease waiting times.
I think we'll talk about this a bit more later, but what you're talking about, I know you're thinking about it from a perspective of streamlining the process and using AI, and which mimics human intelligence, to kind of make that faster. But from my perspective, the way I see it, given that I do a lot of research on climate and sustainability, is that while you're streamlining this, although you're looking at it from an efficiency perspective, it also has impacts on environment and, minimizing the CO2 emissions and your environmental impact, because you don't need to basically use a lot of resources to reach that diagnosis.
Yes.
Or, we're gonna look into this a bit more.
Yeah.
But
so basically, when I get given an objective, that's the first thing. I get an objective as well as the data that they have. And then I build a model based off of that and what they would want as a prediction or an image or a heat map, etc., depending on what is it that the clinicians or the company wants to see. After that, when I've built the model, I've pre-processed data and done the data collection, cleaned the data perfectly for the model to be able to learn it. After that, we start training heavily the model, and we then start testing and validating it with then data that has not been seen, etc. Answering your question about the environment within that workflow, the most inefficient way or the most harmful thing to the environment right now is the training, which takes a lot of time, a lot of computational cost, a lot of data centers, etc. Just because any good model or any mature model at this point in stage right now needs a lot of billion parameters, a lot of data, and that requires a lot of storage, a lot of GPUs to handle, to train, as well even if you were using it as inference later on.
And I think again, just during our coffee conversations, we talk about this, like the difference between training and inference, and how. So if you're doing training once, as opposed to, doing inference, millions of times a day, depending on the model you're using, what does that mean in terms of, environmental impact? And it's not something we've finalized yet, but it's definitely something, looking at what you just said, like the data collection, the training of the model, the validating of it, and then lastly, the inference part. They're all parts. And I think from my perspective, when I look at, for example, carbon accounting or the life cycle assessment of something, this is already quite important to me to understand, the value chain, and then I can start attributing environmental impact to this part, to that part, and this part, and that part. And I know I will have a couple of questions on, like, how can we actually increase efficiency, and what does that mean in terms of like in energy use. So from your perspective, or like, for example, from an efficiency perspective, because you might not look at it from an environmental impact perspective. But I think kind of, leading to that, how resource intensive are some of the projects you've done? So like, maybe can you give us, have you used billions and billions of data points, for example, to train some of your models, or is millions okay for some of the models? Like, how does that work? How do you decide how resource intensive is your model going to be, and how does that affect accuracy from your perspective? So forget the environment perspective from now.
From my perspective, it really depends. So it's based off of, if, for example, if I'm working with oncology department or radiology, definitely they have a lot of data. A lot of data is out there for you to use, that is public and you're able to get your hands on for any type of model you would want. However, certain other diseases is very hard for you to get the data. So we wait for trials and clinical trials to get this data, right? And then there's the concept of transfer and federated learning, where you use a model that has been implemented for other things, and then retrain a few layers or freeze the majority of layers and leave the rest of the layers just for your specific objective, which helps a lot with decreasing computational cost, environmental cost, etc. Because you then are not training billions of parameters, you're training hundreds or thousands, basically. It's a big difference, right? Okay. As well as it now the most upcoming type of frameworks, or is out there right now, is agentic frameworks. Agentic frameworks are multiple agents and multiple models within one framework. That means that you have not less than 4 to 5, and each of those are trained separately, and they're trained on billions of parameters because, again, they're widely public.
And is there a reason we're using agentic frameworks as opposed to one model? Is it because it's more accurate? Or?
It's because it's famous right now in the AI field, if that makes sense.
So it's like an innovative thing that people are looking into. It's not necessarily, we don't know yet if it's, more accurate or more efficient. It's more that it's, okay.
Yes, and it's more human-like. So a lot of the big tech companies are using agentic frameworks because it's more human-like. It answers more as if it's a group of people talking to each other, and then it helps the end user, which is us, feel like you're getting different perspectives now instead of just a perspective that you would want to see. If that makes sense.
That's really interesting and probably something we could look further into in another episode. But I know, for example, the human interaction, I don't know exactly what the job titles are called, but like the human...
Computer interaction. Hey.
Yeah, okay, that. Yes, the human-computer interaction jobs have actually been increasing a lot because... it's a whole field to make sure that bots sound more human-like, and a lot of research goes into this, and it's super interesting, and it's not something I knew of before, actually. And so definitely something that we could explore further in another episode. And so you were talking about, the model, like the data that you would use, and is data the main thing that you would say, dictates how big a model is? Like
definitely.
Okay.
Yes.
So data, and because it takes longer time to train.
Yes. The amount of data you have is how much it will cost training wise. And based off of the data you have, you'll either use transfer learning, where you use another big model to retrain on your model, or if your data is too little, you will then ask to have different type of learnings, which is reinforcement, unsupervised or supervised learning. And usually when you have small amounts of data, you then try to fill in all the gaps, which is creating synthetic data to cover all the gaps until you get more data to fill in these gaps, basically. So either way, it will require a lot of training, or require a lot of computational costs, memory, etc., regardless, because the bar for having a mature model is a lot of data.
So even if you have little data, you might have to compensate that with... Okay, so, there's something you need to look at there and see.
It's a fine line between using unsupervised learning, which means it's unlabeled data, you're not aware of what is happening there, and supervised with big data, basically. More for you to be able to get the right certifications and standards, etc. More people tend to go through the mature model route, which is supervised learning, or start with unsupervised, collect data, and then teach the model more and more about what it should be doing. And then this is where then the agentic framework came into play, where you have supervised models and unsupervised together. They work hand in hand with what you know and what you don't know.
Yeah. And just to clarify, supervised learning would be, it's a model that is based on a lot of data, so it's not really trying to interpret things itself. Whereas unsupervised, you use unsupervised learning when you don't have a lot of data, and you try to
It's not about how much data it is. It's about if you are able to label them. If you know for a fact the connections or the data, how the data interacts with each other. So this column, when it increases, X column increases. That's supervised data, that you are aware of the relationships between the data. With unsupervised data, you're not aware of how they relate or interact. So
and what's the correlations, and you're trying to figure that out.
Yes. So the model helps you find out those correlations and those relationships. And this is why I'm saying usually people start with unsupervised learning when they're not aware of what their data can provide them and how healthy and strong their data is. And when they understand it with the help of machine learning and AI, they further then move on to supervised learning, or well-known now learnings, which they use is federated learning, where you do a bit of both at the same time.
Okay, it's interesting. And I think this is why we were doing this episode. It's quite interesting because there's a lot of, you've already mentioned two things that are quite novel and people are looking into, right? And again, if we're talking about scaling up AI, because it has a lot of advantages that we can use it for. While we're doing all this novelty, you really need to start thinking about how are we going to be scaling it up sustainably. And I know I will ask you about this a bit later on, but actually, to start this conversation, I wanted to ask you to maybe explain the difference between cloud-based and edge-based systems, and maybe kind of from there explain a bit what do we mean by lightweight AI or efficient AI?
Cloud-based is heavily with the words that people use now, which are the fan favorites, basically, is big data. What I mean by that is cloud-based, it's all up there somewhere in a data center where it holds all your data, your models, etc. Needs really good Wi-Fi or just a connection in general for it to be able to do all the training, validation, and inference for you. But embedded AI is sadly till now, we cannot do training on embedded AI. You can only do inference, which is just you giving it your new input and it providing you the prediction you want or the output you want. The difference between that the edge or the embedded AI is that you don't need internet. It's automatic. It's real time. So you get it within seconds. It provides a lot of privacy, especially within wearables, medical devices, etc., because the patient data does not leave his device or her device. It provides a lot of anonymization, etc., etc. But cloud-based is more of there. Then you go into the route of you need security, you need privacy policies, GDPR, etc. Just in case if anything is traveling from point A to a cloud, you need to make sure then that everything's encrypted, it's anonymized. If anything occurs, it can reach the cloud for the patient or the user to get an answer back. Or their data is not broken into in any type of way. So cloud-based, for example, if you're on your laptop, I'm moving away from the medical field. If you're on your laptop and trying to predict what's the weather tomorrow or etc., that's fine. That's the privacy here is just around your location, what you're trying to find, your data that is transferring, like your email, etc. But for example, Edge AI is heavily used for wearables and medical devices for the reason of privacy and security.
Okay. And I think it's also used for simple things that, we use on a day-to-day basis, like Face ID, for instance. Is that
Yes. So that moves more into the lightweight AI, which means a model that has been fully optimized and fully pruned. Pruned by, what I mean by pruned is that any of the billions of parameters that are inactive for a specific prediction get optimized and compressed, basically. For example, there's your facial recognition on your phone. So that's a bit of embedded AI with a lightweight AI. That means that you can unlock your phone anywhere in the world without needing service anything. But that is a model, for example. Another one is any type of smart appliances. So your fridge, your any indoor air quality monitor, just anything that's in your house that is somewhat smart. Your light bulb.
That's efficient and lightweight AI. Yes. It's you've already done the training. It's not being trained on the spot. It's okay. And again, that goes a lot into what we were talking about in terms of environmental impact, and it really, I think, breaks down, all these different models or ways we're using AI and how each different way will have a different environmental impact, and what does that mean in terms of energy use, for example. And I suspect that also leads to a bigger question of, when do we need the models that are, that might have a massive environmental impact, and maybe we don't need that much accuracy in some of the things. And yeah, it'd be interesting to look at that. And then I think talking about environmental impact, and again, you're a machine learning engineer, and I am an environmental researcher broadly, and I know I ask you a lot about this. Like, do you see that in your field, that the environmental impact of AI is something that people are talking about? Is it something that people are starting to talk about? Because I know it's not something that at least you've mentioned to me until I came and prompted you. I'm like, this has a lot of emissions. What are you guys doing about this?
So yes and no. So I think bigger tech companies are taking it into account because they are held responsible for having a lot of data centers around the world. Smaller SMEs where they just want to get their innovative models out there.
Maybe it's not just the first priority. The first priority is let's get this model, let's prove innovation.
Yes, getting it out there, regardless of what that means, regardless of how many GPUs, any computational cost, it doesn't matter. Let's just get it out there as innovative, as fast as possible, because the AI field is growing so much in so many different ways and
really
very
fast as well. Yeah.
And that's because we're using previous models, AI models, to help us build the next best thing. So it's much faster than it used to be, basically. Sorry,
just to nitpick on that. So when you say we're using previous models, does that mean that that minimizes the environmental impact because you're using something that already had environmental impact? Or
yes,
okay, so that's good news.
That is very good news, because a lot of people now try to use already the very big trained models, and a lot of companies are very nice to have it open source for it to be provided. I would like to think that they're doing that for the environment. I'm not sure. But you use these big models that already fully trained and took hundreds of hours to train and billions of parameters and a lot of big computational costs to train, and you're just tweaking it, or you're using it as for transfer learning, or you unfreeze a few layers. That humongously decreases your computational costs.
And I think, again, this goes back to this conversation is massively helpful to me because, as I said, when it comes to doing this carbon accounting or seeing where the environmental impact is, I think, we need to collaborate with each other to kind of, can you break this down to me? Where are you using a lot of computational power? Where is this going? How are you getting from point A to B? And do we need to be using everything you're saying? And can we maybe decrease the accuracy by a certain percentage if it means that we're also minimizing the environmental impact by a bigger percentage. Like those kind of conversations I think are quite important, and it's something we're starting to have.
Definitely. So the biggest computational cost is training, because like I said, it needs a lot of data. All the big innovative models are being trained on billions of parameters, and it takes quite a long time to do that in an effective way. But as well as inference. So inference is, even though you're hitting it once and you're providing an answer, I think that prompts more users to keep on hitting it.
Yeah.
And because the model is still quite big, it sits and it takes a lot of memory, and that alone takes quite a large space in a data center for it to stay alive. And the better the model gets, the more data it gets by inference, by it hitting, it saves your data, and then you'll retrain the data later on, because now you've got other billions of data that are different, and etc. As well as the new models now fine-tune based off of the user. So the model starts learning Nadine Moustafa, for example, or Hanya Ahmed, and how we think and what we wanted to answer us with.
Yeah.
So the fine-tuning also, as I said, it's only a few layers that get tweaked or etc. However, that is still a bit of training or validation as well as inference. So you're opening up that whole cycle all over again.
Yeah.
Which is good for end users, but is not that great for any type of environmental costs.
But again, it's something we need to measure, and that's I think that's where we start, right? Like, one, let's build tools where we're measuring this. Let's have a benchmark of, how to do this efficiently and how to do this sustainably, which, as you said, it's not something that, it's not the first thing that, if you're in machine learning engineer, it's not the first thing you're going to think about. You're not going to think about how to do this sustainably. You're going to think about...
We think about how many GPUs I can get my hands on to do parallel training, or
how to do this faster.
How can I get my model out there as fast as possible for validation, then testing, then inference. Because our end goal is to get more data, to then retrain and to get model out there. Because it's a cycle. It's not more of a, let's train it once and park it. It's more of, let's train it once, validate it, test it, and then use it provide it to users, and users to use it for inference a lot, and then the cycle starts again.
So I think, I don't know if you have anything else to say, but I think the ending of this episode is basically to say that we need to start looking at, building those benchmarks, building those tools to kind of start measuring this environmental impact depending on what you're doing. Looking at it from a trade-off perspective, as we do with a lot of environmental choices that we have. So, we could technically be like, let's stop producing anything that's, that has any sort of environmental impact. But obviously there's a trade-off, right? If we stop aviation tomorrow, there's a trade-off. The trade-off is that there's a lot of globalization that happens because of aviation. There's a lot of jobs that are produced because of aviation. There's a lot of cultural awareness because of aviation. And there's a lot of collaborations, for example, globally that happen because of aviation. And so I'm not going to list all the advantages, but what I'm trying to say is that it's important to start there, start measuring, and then we can start looking into those trade-offs. And I think that's probably how we.
Yeah, I think I have a question for you actually before we end this. Is that realistically, right now, the way that we might calculate the environmental costs for training, etc., is based off of just data centers, right? The energy that it pulls, electricity, the ACs that it uses, GPUs, etc.
Mm-hmm.
Do you think there's there's more things that we need to take into consideration? Is there other things that we personally as engineers don't even take into account that you would be taking into account?
Mm-hmm.
Or Yeah.
There's a lot of things we would take into account. So, for example, water usage, if there's any, there will be. So that's one. One that I'm quite interested in is the materials that we're using and where are we getting them from. Because, there's a lot of studies out there about the critical minerals that we will be using, or we're saying we need to reach our net zero targets. And, that number is a lot. And do we have access to all these minerals? And again, I could go on about this forever, but short answer is that there's a lot to look into. But I think just starting somewhere is important. And I say this quite a lot. We don't need to be perfect now, but we need to start.
Yeah.
And then we can aim for perfection.
Yes.
But we have a lot of targets. We have a lot of plans to reach net zero, but unless we start doing and learning by doing, we're not going to get there. Next targets are in 2030. That's 5 years from now.
Yeah.
That's nothing.
That's too close. Would we be able realistically to create a CO2 emission calculator when I'm building my model, I know how many GPUs or parameters I'm using? I just want a little pop-up that says, hi, this model will be emitting this amount of CO2.
We can, and it's something that people are looking into a lot, doing carbon accounting is a whole field, I've personally talked about it quite a bit in different episodes in this podcast. And again, carbon accounting is so different depending on which industry you're doing it for. Mm-hmm. And we need to, and as with anything when it comes to environment, we need a bit more granular approaches. And so this is why I think this conversation is quite important, because, okay, we know how to do carbon accounting in general. As you said, we're going to measure the energy use, we're going to measure the water use and so on. But we need to kind of have methodologies or ways to do this accurately for AI, and then we need to do this accurately for other things. And it's more accurate for industries that are more mature, but as we mentioned, AI is something that's being scaled up and it's growing, super
very
fast.
Yes.
And in this episode alone, you've already mentioned 3 novel models and things
within
that people are
the
looking
last
at.
Year. Exactly.
And so just starting somewhere and being flexible and adapting it to whatever is going on later is where we should start. And I think
and we can use AI to help us adapt quicker.
Yeah, we can. And I think we can
lightweight AI. Hopefully,
I think we can end the episode on that note, where basically we're vouching for more cross-disciplinary projects and kind of looking at the environmental impact of things regardless of where you're working, right? Whether it's the medical field, as you do, for example, or specifically within AI and machine learning. And thank you so much.
Thank you so much for
joining me today.
Thank you so much for having me.
Thanks everyone for listening to our podcast.
Thank you.
Thank you for tuning in to the Energy Futures podcast. Here at Energy Futures Lab, we are dedicated to addressing global energy challenges through pioneering research, innovation, and advocacy. To learn more about us and the exciting projects we are working on, visit our website and follow us on social media. If you enjoyed this episode, please like and share and subscribe to stay up to date with our latest content. Until next time, stay curious.